Find the eigenvalues and eigenvectors of the matrix below. Now, remember, eigenvalues, the word eigen is German for the word own. Alright? So you're finding the vectors own values. The matrix sees own values and the matrices own vectors. Now, here's a formula for this. Here's a formula here that says if you take the vector, the vector is A, and you multiply it by its eigenvector V, you get the same thing as if you take the eigenvalue of the matrix lambda and multiply it by its eigenvector V. So basically, the matrix multiplied by its own vector is equal to the value of the matrix multiplied by its own vector. Right? Matrix times its vector equals the value of the matrix times its vector. So the matrix has a value, its own value, which we call the eigenvalue. Eigen, German for own. Alright? Now, here, if we subtract lambda times V from both sides of the equation, we have the matrix times its vector minus the eigenvalue times its vector equals 0. Now, we can factor out the eigenvalue V times the matrix minus its value. We factor out the eigenvector, the vector of the matrix. So the matrix minus its value is equal to 0. But hold on. The matrix here, it is a matrix, but the value is just a number. You cannot subtract a number, one single number, from a matrix. It has to be matrix minus matrix. So here, what we're going to have to do is multiply lambda, the eigenvalue, by the unit matrix having the same dimensions as the matrix. So multiply by 1, 0, 0, 1. So what we have is lambda times I, the identity matrix, which is unit matrix. So we say this is the vector of the matrix times the matrix minus lambda I is equal to 0. Alright? So we're going to be using this equation. Now, let us write this up top. V times the matrix minus lambda I. Let's write it up here. V times the matrix minus lambda I equals 0. Alright, let's get rid of some of these rough working that we did earlier. Remember, I'm not jumping straight to finding the eigenvalues of this vector just yet. I want to explain the argument behind doing so. Now, if we have this situation, it means A minus lambda I will turn out to be a matrix. Now, suppose we multiply both sides in order to find the eigenvector V. We multiply both sides by the inverse of A minus lambda V. So we have A minus lambda V inverse times this is equal to 0 by A minus lambda V. So what we have is the vector, lambda I, not lambda V. My. It's lambda I. A minus lambda I, A minus lambda I. Okay. The vector times A minus lambda I invert times A minus lambda I is equal to 0 times A minus lambda I. What to that? A minus lambda I invert times A minus lambda I would give you a unit matrix. Alright? So V times the unit matrix is equal to 0. Because 0 times A minus lambda I invert. It should be inverse. Right? We're multiplying both sides by the inverse of A minus lambda I. This and this is the same thing. So the inverse of the matrix times the matrix itself gives you the unit matrix or the identity matrix. 0 times this gives us 0. Now, this would mean that V, the eigenvector of the matrix, is 0. But that cannot work because it should be a matrix that is not equal to 0. So therefore, A minus lambda I should not be invertible. Right? So for that reason, A minus lambda I you should not be able to find the inverse of A minus lambda I. Right? So if you remember the name of the type of matrix that is not invertible, it is called a singular matrix. And what is a singular matrix? One whose determinant is equal to 0. You cannot find its inverse. So A minus lambda I. The determinant of this is equal to 0. Alright? So the determinant of A minus lambda I must be equal to 0. So using those arguments, let's look at this. The matrix A is 3, 2, 5, 4. So we have 3, 2, 5, 4 multiplied by 3, 2, 5, 4 minus, not multiplied by. Where I get multiplied by from? Right? The matrix A, this is the matrix A, minus lambda times the identity matrix 1, 0, 0, 1, right? the determinant of that. I have our two vertical lines to show that it's the determinant. That's another way you can write the determinant instead of det. It's equal to 0. Alright? Let's see what happens here. So we have 3, 2, let me write it down a bit further. 3, 2, 5, 4 minus, let's multiply lambda by this matrix now. Lambda 0, 0, 1 is equal to 0. The determinant is equal to 0. Alright? So now, what happens after that? What we have is that the determinant of the matrix. So you subtract the corresponding elements, 3 minus lambda. So 3 minus lambda. Then we have 2 minus 0. 2 minus 0. But that is just going to be 2. Then 5 minus 0. 5 minus 0. But that's just 5. And then, oh, this is lambda. Why do I put 1 down here? I put 1. Lambda times 1. Then lambda times 1. Then we have 4 minus lambda. The determinant of that is 0. See that? Alright, so after that, how do we find the determinant? We have these multiplied minus these multiplied, alright? So 3 minus lambda times 4 minus lambda minus 2, 5, 10 equals 0. Alright, so how does this go now? Let's multiply out the brackets and so on. 3 by 4 is 12. 3 by negative lambda is minus 3 lambda. Negative lambda by 4 is minus 4 lambda. Negative lambda by negative lambda is positive lambda squared minus 10 equals 0. Alright. So lambda squared minus 3 lambda minus 4 lambda, that's minus 7 lambda. 12 minus 10 is what? 2. Plus 2 equals 0. So we can now find lambda. Now, how are we going to do that? Can this be factorized? So it's a quadratic equation in lambda, right? We can find lambda. Let's use the AC method. A would be 1, B would be negative 7, C would be 2. Because this is similar to ax squared plus bx plus c equals 0. Remember that. in this case though, instead of x squared and x, what we have is lambda. Alright, so the number that multiplies lambda squared is a, that's 1. The number that multiplies lambda is negative 7, that's b. And the number that multiplies lambda to the 0, it's 2. This is really lambda to the 1, you know, and 2 lambda to the 0. Alright? But anyway, you don't see those. Those are invisible. You don't bother to write them. So how does this go now? We need to find two numbers that multiply to give you 2. They multiply to give you 2. Add to give you negative 7. Well, it doesn't seem like it can be factorized. So we have to try another method. We could try using completing the square or the formula, the quadratic formula, right? So let us use the quadratic formula if we can find it. Alright. So here, the quadratic formula. Instead of x, it's lambda. Lambda equal negative b, that's negative 7, plus or minus the square root of b squared, that's negative 7 squared, minus 4 by 1 by 2, all over 2 by 1. Alright? So lambda equal 7 plus or minus the square root of plus or minus the square root of 49 minus 4 2's 8 over 2. 49 minus 8 is 41. So this under the square root sign would turn out to be 41. 41. 7 plus or minus the square root of 41 over 2. Alright. So lambda would be what now? 7 plus square root of 41 over 2. What is square root of 41? Let us see. Square root of 41 equals 6.403. Alright. So it's 7 plus or minus 6.403 over 2. Alright. So lambda equal. Let's get back to our calculator. So we have 7 plus 6.403 equals over 2 equal, we have 6.702. 6.702, and lambda is also equal to see how this goes. Yeah, so lambda is also equal to 7 minus 6.403 equal over 2 equal 0.299. 0.299. Yes, so these are the two eigenvalues. 6.702, 0.299. So far we see that lambda equals 6.702 and lambda is also equal to 0.299. My. Let me rewrite this 0.299 here. The 6.702, let me just check back. 6.702, right. Now, those are the eigen values. We want to find the eigenvectors now. So, here, the vector times a minus lambda I is equal to 0. Alright? So, a minus lambda I. What was a minus lambda I again? So it's 3 minus lambda 2. So it was 3 minus lambda 2 5 4 minus lambda. We have 5, 4 minus lambda times the vector. What would be the vector? Let's say, let's call these x, y, right? So we see that this v times a minus lambda I equals 0. Remember, we wouldn't be able to multiply them if we put v to the left of a minus lambda I. And this is a minus lambda I, right? A minus lambda I. So we have to put v to the right. Alright, so that is equal to 0. So let's multiply them out. But we want to work out the values with the known lambdas first. So 3 minus lambda. 3 minus. So here we make lambda. We use one of the lambda. Lambda equals 6.702. Suppose we use that lambda. We'd have 3 minus 6.702, 2, 5, 4 minus 6.702 times x, y equals 0. Alright? So, what we have here now is 3 minus 6.702. Alright, I'll do it off screen on my calculator. 3 minus 6.702. What is it? Negative 3.702. So we have negative 3.702, 2, 5, and then 4 minus 6.702 will give us negative 2.702. Alright? Times x, y equals 0. But this 0, you could even write it like this. Alright? So, negative 3.702x plus 2y times 5x minus 2.702y equals 0, 0. So up here equals 0, down here equals 0. Alright? And then we solve this. Now, we can solve it using the normal elimination method, or could use a matrix method. Since we're dealing with matrices, let's do that. So we have negative 3.702. Let's write it in matrix form. Write it back like as it is up here. So here, instead of multiplying it out, right, like this, we have it in matrix form already. So let's write it like that. Negative 3.702, 2, 5, negative 2.702, we have, oh no, alright, times x, y equals 0, 0. Oh no, I lost concentration. What am I doing? It wouldn't be this. My. It will be negative 3.702x to y. Then we have it's plus 2y. Then it would be equal to 0. Just rewriting the top. 5x minus 2.702y equals 0. But the thing is, you know that the left contains x already, and the y contains y. The right side contains y, so you don't have to write them. Alright? So all of this is plus, and you leave this minus sign equals 0. So let's just do things like this. What we have, we can put it in a little square bracket, draw our line, and put the right hand side like this, and we line up the zeros. Alright? Alright, so we could use the elimination form. Gaussian elimination form is going to be a bit more complicated, being that we have fractions or decimals here. But once you solve this, you will get the eigenvectors corresponding to lambda equals 6.702. Alright? Suppose we divide both sides by 5. If we divide, call this row 2, this is row 1. We divide row 1 by 5. Row 1 times 1/5, 1/5 row 1 leads back to, no, 1/5 row 2, 1/5 of row 2 leads to our new row 2, and we make row 3 remain the same. Alright, so this is 1, this is negative 2.702 over 5. 2.702 over 5 will give us 0.54, negative 0.54. And of course this remains 0. This is 0, right? Now suppose we divide and say row 1 times 1 over 0.702, 1 over negative 0.702 gives us our new row 1. What would happen? When we divide negative 3.702 by itself, we get 1, and then 2 over 3.702, and negative, we get 0.54, so it's negative 0.54, it's what? 0.54, when we divide 0 by it, 0 remains as it is, we have 1, negative 0.54, alright, and 0 is here. Alright, now here, you see, both contain the same things as expected here. Now, there is no specific value for x and y. There will be no specific value. So, let x be a certain number. Simplest number is 1. Let x equal 1. Then y would be, now if we let x equal 1, let's rewrite this first. 1 minus 0.54. That's row 1. 1 minus 0.54 is equal to 0. Right? But 1x minus 0.54, y is equal to 0. Let's put in the x and y. Then it means that x is equal to 0.54y. Right? So, if x equals 1, then 1 is equal to 0.54y. So y would be 1 over 0.54. So when x equals 1 over 0.54 will give us what? 1.852 equal 1.852. So our eigenvector is 1.852. So one of the eigenvectors v is equal to 1 and 1.852. Oh my. And 1.852. That is when lambda equal 6.702. This is what happened. Alright? See that? Now let's use the other lambda and see how it goes. Let's erase these things that we had under here before. Now, what we're going to do is let lambda equal 0.299 this time. What would that? Alright. So we have 3 minus lambda. So this would be 3 minus 0.299 equal. So what we would have is 2.701. And we have 2, then we have 5, then we have 4 minus lambda, which is 4 minus 0.299, gives us 3.701, right? 3.701 x, y equal 0, 0. Alright? So when we multiply out the brackets, we would have 2.701x plus 2y equals 0 and 5x plus 3.701y equals 0. Alright, let's write it in a matrix form now. We already know that on the left is x. We don't want to crowd the thing without any x and y's. Alright, use a square bracket here. It says equals 0. So to separate the left and right hand side of the equal sign, we do a vertical bar. And we know this is plus and plus. Alright? Now, let us do a little elimination with this. Let us say we have 1 over 2.701 row 1. Remember, this is row 1, row 2, which will lead us to our new row 1. Alright? When we divide 2.701 by itself, we have 1, and then we have 2 over 2.701, which is 0.74. So we have 0.74. 0 over 2.701 is just 0. Right? And then 1/5 of row 2 will give us our new row 2. Alright? So 5 over 1 is just is 5 over 5, because 5 times 1/5 is the same as 5 divided by 5. You multiply a number by 1/5, same as the number over 5. So this is 1 minus, and then 3.701. 1/5 of that is 0.74. 0.74. As expected, we would have the same things here. Alright. Now, remember, here, when we have in this form, it means 1 times x plus 0.74 times y equals 0. Right? Oh, let me just rub off and erase part of the work I did down here earlier to make space. So, x plus 0.74 y equals 0. That means x is equal to negative 0.74 y. Now, when x equals 1, because there is no specific number for x and y, right? There's just a ratio, a relationship between them, right? So, when x equals 1, you could use any other number, you know. But 1 is the simplest. When x equals 1, what happens? 1 is equal to negative 0.74 y. So y equal 1 over negative 0.74. And then 1 over negative 0.74 is negative 1.35. Negative 1.35. So, what we have is 1, negative 1.35. So, V, we could call it V1 and this is V2, since it's two different V's. V2 is 1. What was it again? Negative 1.35. Negative 1.35. That is when lambda is 0.299. Lambda equals 0.299. So we have our two eigenvalues that correspond with, and the two corresponding eigenvectors. Alright? So these are what we have. Eigenvalues and the eigenvectors. So here now, as we said, the eigenvalues minus the eigenvectors. We find the determinant of this. We get 0 as the determinant. And here, we have the two eigenvalues for 3, 2, 5, 4. Right? Now, a minus lambda I is this. We have 3 minus lambda 2, 5, 4 minus lambda. When we subtract these, we get this. And then the vector 2 in order to find the, when we find the eigenvalues, in order to find the eigenvectors, we have each eigenvalue separately. For lambda, we multiply by the vector. Sometimes they call it V1 and V2, right? I put them this here as X, Y, and you use a matrix method elimination to find out what those values are. And there's no specific value for X and Y, right? You put in one value, let X equal 1, and you find Y. You could have also done Y equal 1 and find X. Alright? So that's an eigenvector. You have your eigenvalue and eigenvector that correspond with it.